All right. So today the talk is going to be balancing cost and quality in FMware deployments. Just to introduce myself, my name is Kirill. I am an applied AI researcher / engineer, working on different projects. A lot of them currently right now are about deploying FMs, using FMs in different applications, specifically software engineering, and then also had a chance to work on the demo you just saw, like the application there. So what this talk is going to be about is more real-world considerations and how to deal with them when you're deploying FMs in whatever application or whatever use case you have. So just to give a quick overview, first and foremost, how do we choose the correct FM? We're going to talk about what are the concerns of what's selecting it. Like if you're developing some kind of software application, you just want it to work, what do you do? There's a bunch of decision criteria you can look at. There's the cost and quality argument, because at the end of the day, we all know OpenAI is expensive. Azure is expensive, AWS is expensive. So what can we do to mitigate those things? Afterwards, we'll talk about just the whole concept of deploying FMs as part of FMware. There's one very useful, trick / feature you can think about to make your decisions easier and then also bring down costs. And then I think majority of the presentation is going to be talking about a survey of different methods and challenges that have people attempted already in this field successfully, some more successful, others less, such as, for example, we listed some here like model enhancement, synthesis and ensembles, and the one that I want to focus the most on is the last one, predictive, non-predictive routing. And by the way, just at any point, feel free to raise your hand, ask a question, we can stop. We should have enough time for everything. So let's get to it. Part one. So choosing the correct FM. One of the first decisions, do I go with Llama? Do I go with GPT, Anthropic, Claude? There's many different choices. For example, just on Hugging Face alone, which is this hub for a lot of MLs, there's around 700,000 of models you can get. This is actually pretty old information. It's back from I think June. Now there's probably way more than that. And different models there with different capabilities. There's bigger models that can do instruction tuned. There's reasoning models. There's summarization, embedding, so on and so forth, from as small as 125 millions of parameters to a couple of 100 billions of parameters. Also, one big important thing is licenses. I'm not sure if Gopi has talked about it before, but software usually has some kind of license attached to it. Famous ones is BSD, GPL, MIT licenses, and they all have different permissions in terms of can you use them commercially, can you use them in academia, open source, and so forth. So things I've taken into account. One examples of things I just mentioned, for example, on the left, have the FM capabilities. Instruction tuning, that's a specific thing that the model should be able to do. Some of them are not instruction tuned, they're just pre-trained. They have the text completion. Plan and reasoning, recent model from OpenAI, O1, very good at reasoning. Compare that to, let's say, first GPT 3.5, probably not so good. Tool use support, that's been on the rise. Being able to use, for example, output things in a JSON format, or call for support of tool use in JSON format. And actually, this is a very good example here, fill in the middle capability. One of the talks you'll see on Friday actually makes use of this, and you'll see why. But when we were working on this project, we were basically only limited to 2 models that supported this. And that's another thing, that's what limited our selection. For the model size, it's pretty self-explanatory. Models can be small, big, it's about it, anything in between. So that depends on what kind of compute you're using and what's your use case. And of course, licenses, as I mentioned, there's many different ones. Make sure they're applicable to your use case so you don't get sued later on. So that covers kind of most of it. Now, if you focus mostly on specifically deployment of FMware, there's 2 things you want to be focused on. Is one, capabilities. So just what we talked, what do you want it to do? And second one comes into play now is the compute costs and limitations for FM inference. So for example, just a couple of, you can see look at the top. What if you're deploying your FMware app on an iPhone, right? An iPhone, for example, iPhone 16 has the 18 chip, which has an NPU with about 35 trillions of operations per second. That's the tops. Pretty cool. Seems like a lot. Compare that to NVIDIA A100. Now it's already second. Like, it's not the best out there. There's H200 out there, which is even higher. But that has 312 teraflops of, teraflops, which means floating point operations per second. So very different hardware. So as well, iPhone, limited RAM, NVIDIA A100, 40 gigabytes, sometimes 80. So that will also influence the kind of model you can use. Now we come to this dilemma where, larger models, good, very capable, GPT-0, let's say Llama, big llamas, can do a lot of things, and you can see on this little, I don't have a pointer here, on this little diagram over here, for example, this is actually taken from Llama 3 technical report. You can see that a Llama 3, that's 8 billion parameters, performs considerably worse than Llama 3, which has 405 billion parameters. So there's a capability gap. But at the same time, you can probably fit your Llama 3 8B on your iPhone in terms of the memory. You can do the same with 405 billion version. And at the same time, the compute that you need to run these big models costs a lot. NVIDIA can make enough of them, and that's why they're the most valuable company right now, just because everyone wants the big and the better models, and that requires a lot of GPUs. So how do we balance these two things so we can get kind of the best of both worlds? And that's when we go to kind of this central paradigm that I'm going to discuss when you're deploying FMware. And that is, from the perspective of your overall system, FMware, your FM itself can be treated as a black box. As long as you can serve the requests successfully, you don't care what it does. You don't care if it's one model. You don't care if it's two models. You don't care if it's Llama or GPT. From a FMware perspective, you just want it to work. Okay? And this kind of paradigm helps us to think of different ways to optimize that black box, but at the same time maintain whatever quality of outputs that you want. So as I mentioned over here, notice the terminology acceptable quality. It's not perfect. It's not exact. It's good enough. So as long as you can get good enough outputs, that's great. That's what you want. And then from there, we can then think about ways to optimize it. One example, as you see later, is use a combination of models. You don't have to rely on one single thing. You can try different ones. And that's exactly where we're going to our next part, which is a survey of executing method and challenges. So there's a good paper that came out early this year, Router Bench, and they kind of broke it down to three main categories. One is model synthesis. And this is kind of, I guess, the initial first naive way to solve this problem. And that is just to improve the model that you're using. This can be done many different ways. Classical, fine-tuning. There's preference learning. There's some of the methods I'll mention later, GPO, RLHF. There's also, I guess we'll call it non-evasive methods, such as prompt engineering, where you engineer your instructions such a way to try to get the desired output. And as I mentioned before, chain of thought, tree of thoughts, many different ones, I think, that were discussed during previous sessions. Next one, synthesis. A bit of a different approach. In this case, what they do is they use the outputs of several different models, merge them together in one way, shape, or form, and then try to improve the output that way. There's also several methods available, and it typically requires multiple inference rounds, meaning you have to get first output of the models, then you have to combine them together somehow. Last but not least, personally my favorite, routing and layering. So what that means is that we will select the appropriate model based on the input typically, or the output. You'll find in a second. There's typically two types, predictive and non-predictive. I'll explain a bit later, but reason why I like this one is because we can avoid that initial model inference, which is expensive. And generating tokens is expensive at the end of the day, input and output. And if we can avoid that initial step and just go directly to the model that we think is going to be the best, that's going to be the ideal case. So, but first, we'll have to get there. We'll focus on model enhancement first, just kind of give a quick overview. I'm sure a lot of these things are probably nothing new to a lot of people, but I want to make sure we're all on the same page here. So, kind of general overview of model enhancement. We have 3 different types. I broke it down. One is parameter optimization. What I mean by that is you're directly optimizing the model weights. This is your typical machine learning training. For example, semi-supervised fine-tuning or just supervised fine-tuning on top left. You have your data, you have your pre-trained LLM, you train it, wow, it can do new things. Straightforward. More exotic approaches that have been used recently, it's called alignment tuning typically. RLHF stands for reinforcement learning with human feedback, is where you try to teach the model to reply the way you want it to reply. So it's not just in one input to the output, now you're trying to influence how it generates the output. A bit more newer technique to that, I think has been used, the latest llama training model, like basically a lot of the latest LMs use this, is DPO, direct preference optimization. It's the same thing as RLHF, except now you're just bypassing the need for training a reward model, and you're using your LLM as the reward model itself. Very interesting stuff, highly recommend if anyone's interested, take a look into it. But that's mainly the parameter optimization methods. Expensive, like they require a lot of compute, you're actually training the models. Mixing it up a little bit, architecture methods. One example is mixture of experts. There's a bunch of models floating around that do that. And what they do is that it combines multiple, I guess, models in the multiple sub-neural networks, we'll call them, inside the overall architecture, and then it has a specific gate unit which will route to a specific expert. So people try to use this. There's one paper cited right there, where they would try to route the input queries to the appropriate subnet at runtime, and there's different ways to do it. But that also requires training. So going back to the parameterization, these all require training and learning. Last but not least, probably way more effective than the previous 2, and require least amount of effort, prompt engineering. Again, this is just changing your instructions to try to get the desired output. Top of there, you'll see it's tree of thoughts from the tree of thoughts paper. Trying to, I guess, develop the correct reasoning to arrive at the desired output. At the bottom is self-consistency. Think of it this way: we're just generating multiple outputs, and we're trying to select the one which is the majority voted. I think one of the questions for previous talk was talking about how do you end, let's say, end the conversation with the agent. One of the proposed solutions was majority vote on the solution. This is a similar thing. It's just now you're doing it with prompt engineering. But these are just some of the methods I mentioned. There's different ways you can think about it. There's like a whole other stack of papers you can go through. It's a pretty active field of research. Only problem with all these things, they're model and scenario specific. So if, say, for example, you want to deploy a model or 2 models. One model would be for, processing financial reports. The other one's going to be from translation. And the way you train and tune both these models would be different. And it's also going to be very specific to the model you're training. So if at any point you want to change your underlying LLM from, let's say, let's say Llama to a Falcon, an older LLM, then you have to repeat the whole process again. So we want to try to avoid that. It's very expensive, very intensive, but it gets the job done at the end of the day. Any questions so far? Good? Perfect. Moving on, synthesis. So just as I mentioned before, this is when typically you would get multiple outputs and then you find a way to combine them together. One example, on Blender, exactly what it says. It collects candidate outputs of several FMs, does a bunch of post-processing, ranking them together, combining them, comparing, so on and so forth, and then in the end it merges the top-ranked outputs, combine the train, and then you get your final desired output. I'm just going very top level of this. If you're interested, you can read the paper, it's good. But the general idea here now is that 1, we generate multiple outputs from different LMs, and 2, we combine them in one way, shape, or form. Another example, blending is all you need. What a clever title. Similar idea. The output is generated as a combination of outputs, but they went about it more of a probabilistic approach. I don't want to go too much into it, but the highlighted parts here. What they're trying to say is that they implicitly influence the output by blending individual chat AI strengths, and they collaborate to create overall more engaging conversation. So similar idea, different way to go about it. Once again, in this case, we have to generate multiple outputs from the LLMs. So it is a bit computationally intensive, and when you're concerned about deploying into production, we're talking about costs, and we're also talking about latency. So latency is a user experience problem, and if we have to generate, let's say, outputs from 10 LLMs, and some are big or some are small, that will take a lot of time. And it's also very expensive. So ideally, we also want to try to avoid this or see if there's a way to mitigate. And we'll find out there's another approach to this, which is, again, routing. Personally, my favorite, and we'll find out in a second. So there's two types of routing. One is non-predictive routing, and then there's predictive routing. So if we focus first on our left, non-predictive routing is concerned with collecting outputs of multiple FMs, again. But the way it does it is we don't do it in parallel and just combine them together and look which one's better. Instead, it's usually done sequentially. So let's say we have a list of models, A, B, C, D, E, F, and you want to say, okay, how can we get the right output for least amount of cost? Okay, let's start with the simplest model, get the output. Is it correct? Is it satisfactory? No? Okay, try the next model. And then the next, and the next, and the next, until we reach the good result. And how do you measure it? There's usually some kind of quality threshold, be it comparing the similarity, or you can, you have the user mark whether the answer is satisfactory or not. Different ways to do it. Downside, increased cost and latency. Again, many rounds of inference seems to be a common theme so far. All the methods we've seen so far, except for the, first one, requires multiple rounds of FM inference, which is expensive. But let's look at some examples of that. So one paper, it's called Tabi, one approach. It actually was proposed for discriminative models, not generative, but there's papers that also work this on generative. But the main idea here is that there's a great diagram all the way at the far right, kind of get you just general idea, where they start with a smallest, cheapest model, and they kind of go down the chain and generating outputs until they're satisfied, or they think or it just runs out of, it's not good enough in the end at all. And there's a good diagram over here. You can see the percent of correct prediction versus the number of parameters. And you can see that if you use the smallest model, you have to a certain extent, majority of things can be covered by, let's say, the small model, but then if it can be, okay, now can be covered by a more expensive, larger model. Okay, if it can't, move on to next, and so on and so forth. So this is one example of this approach. Second one, Frugal GPT, very aptly named. This paper just kind of gave a general overview of different methods you can use non-predictive routing to improve, improve your costs by lowering them and still get the same output. And it's just a collection of different methods you can try. Prompt selection, maybe you can find a similar example. One interesting solution they offered is if there's a completion cache, where they would cache previously similar examples and say, okay, is this one similar to what we saw before? Can we reuse it again? Sure, great. Model fine-tuning comes in once again. That's approach as well. And then LLM cascade is exactly what we saw just in the previous slide. Just try models one by one until we get where we want to go. I think this is one of the papers that actually started this whole, not craze, but a lot of papers cite this paper as initial thing for justifying their work on, be it model routing or LLM cascade. I think this actually came out just about the same time when ChatGPT rose to fame, and they're really trying to find ways to not pay so much to OpenAI. So, as I said before, those too many methods, limitations, increased cost and latency due to main rounds of inference. Now let's look at predictive routing. And then we'll spend more time on this. And the reason why we like it is because what it does, it selects the model based on the input request. So the output of the foundation model is not required, meaning that we never have to do that initial pass. We can just look at what we're given, Okay, and then we can pick the model. Typically, this is implemented using some kind of prediction models. Your classical classifiers, if you name it, you can probably use it. And you need some kind of data set that's preference data set, where given some kind of output, you know which place to route it to. Two things though, there's two limitations you can see on the screen. We're gonna kind of go back to this later, but one thing is that just like any machine learning model, the performance is often limited by the quality and the generalizability of training data set. So if the query that comes in is completely dissimilar to what has been seen in the previous training data set, then you might have issues. And last but not least, when these models are deployed, they're static. If you want to, let's say, deploy a new model or change the model or add something else, you usually will have to retrain them. There's ways to deal with it, but that's what you have to, unfortunately, pay the price. So let's look at a couple of examples. One is called Zooter. You'll see a common theme around here is that what they do is they train a reward model to rank different input queries. Then they train the reward model through the knowledge distillation. And then over here, just kind of you can see the heavy part is the reward model ranking, where they rank different response depending on the model, assign a tag, and it's a whole life cycle. And then in the end, though, it's very simple. If you look at the orange / kind of brownish, I guess, path, the inference is just the query comes into Zooter, and then the Zooter then determines which LM it goes to, and then you get the response. So training takes time, difficult, but when you deploy it, it's very simple, elegant, and we're saving a lot of compute. Similarly, another paper, Hybrid LM, does basically almost the same thing, just slightly different. It's using a predictive router. It encodes the input query using a DBERT-style encoder. And then they train two models. One is a deterministic router, one is probabilistic router. The differences between them is that how they define the labels for which models to use. So one of them can be like, okay, only use this one, don't use nothing else. These are called usually one-hot encoded. The probabilistic usually says, okay, there's a probability that this query, let's say you get 20% chance that it should go to this one, and 80% chance it goes to the other one. So at the end of the day, it's the same kind of solution. But once again, we're training some kind of model to give us the final label where the query should go. And in this paper, one important thing to note is that they're using BART score, and we'll come back to it very soon, but that's just one thing to remember. Router LM, probably one of the latest papers on this topic, released by Anyscale and some people at, I believe, Berkeley. But they kind of went further, and they tried different ways of training these predictive routers, from very light to very heavy. One was just a similarity-weighted ranking, which is an ELO rating of which models we want to use. Another one is metric factorization method. If anyone's familiar with recommender systems, taken straight from there. Other one was a BERT-based classifier, mass language modeling, and lastly was just training a causal LLM, an autoregressive model to give you an output. A couple of interesting things from this one is that what they notice is that, and you'll see this again in the challenges of this approach, the performance of the routers highly depend on the data. And take a look at the graph on the bottom, this empty bench. So empty bench is one of the benchmark data set that they used to evaluate. Keep in mind that these models were trained, there's actually two data sets that they used. One is called Chatbot Arena dataset, where user would submit a query, you would get processed on an LLM, and there usually be two LLMs, and you have two outputs, and then the users can decide which reply I like better, A or B. And this was done across different types of models. I think there's probably 13 or 15, and there's quite a bit of data. So that's one of the data sets they used, and that's the non-augmented version, we see before augmentation. So at the end of the day, it's a conversational data set. The other data sets they use to help augment this, this first benchmark is like typical machine, I guess, LLM benchmarks for question answering, and some of them were also, I think, GSM 8K, which is grade school math. And those type of questions were multiple choice. So there's two different types of domains. One, natural language. The other one is more of multiple choice questions. And if you look at these graphs, especially this one over here, that's trained only in conversational data set, you know, it's somewhat worse than, you can see the red one, BERT. It's worse than random, like a random router, basically. Some are better. But then what they found out is that when you added more diverse data to it from these other benchmarks, well, look at that. Our performance improved quite a bit. But if you look at, for example, the graphs over here before augmentation, and remember that these, for the routers in the left side of this graph, they were only trained on conversational data. Meanwhile, both MMU and GSM-8K, they're multiple choice question type benchmarks. And look at that, the performance of our routers usually generally are around the random baseline. So this shows quite a big difference in terms of, I guess, dependence on the router, on the training data that it sees. If it sees conversations, it doesn't do too well at routing queries that are multiple choice questions, and vice versa. Which is why this is actually one of the big limitations of these routers is the fact that the kind of data you use is very important. And here we go. We're going into more challenges and limitations. So, as I mentioned before, they're usually based on training a classifier, which is an ML model, using a preference data set. On the left, we have all different methods we discussed. On the right, we have, or it's vice versa, actually. But yeah, you can see on the right, we have the different preference data sets that have been used to train this. There's a bunch of different ones, and they're from different domains from, let's say Chatbot Arena is the one I mentioned, which is discussion-based. Router Bench is kind of another data set which combines a bunch of different benchmarks in together. But the point is, it's a very traditional ML problem. So, two problems as I mentioned before: reliance on the quality of the preference data set, and the update process complicated. You know, what can you do? First one, well, I guess I covered actually in these slides. But as you can see over here, the difference between the performance on the conversational benchmark versus multiple choice benchmark in the graphs. And then the other problems we usually see is just traditional ML problems. Acquiring preference labels is difficult. You know, Chatbot Arena is great. Why? Because it's crowdsourced. You know, the actual authors didn't have to go and label the 10, 20,000 of labels themselves. Other people helped. Other common problem is, you know, out-of-domain generalization. You know, are the preference labels actually properly reflecting the strengths and weaknesses of every foundation model? You know, if you, for example, compare the OpenAI's O1 in reasoning compared to, let's say GPT 3.5 from 2 years ago or 1 year ago, very different. How do you measure that? And last, as I mentioned before, like the graphs you can see, it's how well does a generalized to unseen type of input? And that's another big problem. But these are all traditional ML challenges, and there's ways to mitigate this. The other part of it, updating them is fairly complicated. Whenever a change is required, you know, you have to retrain the model, you have to update the training data, you have to make sure the post-parsing is correct. You know, they can see the ML life cycle. You have to repeat the whole cycle again. Double check that the previous learned knowledge is still there, or at least is still reflective of what you need. You know, and how do you deploy them? That's another thing. Typically, this will be done through software updates to a smartphone. You know, iOS 18 coming out with Apple Intelligence really soon. That's one way to do it. But either way, it's not like a quick and done solution. There's processes that have to be followed behind it. So it takes time. But, you know, what can you do? So I'm actually coming up on my time here. But if there's anything you want to take away from this entire talk, unless you're still awake, that is, first thing foremost, you know, it's important to consider FM selection criteria and pick accordingly. There's typically no one-size-fits-all when you're considering costs, when you're considering your compute limitations, and your FM capabilities. Prime example, type of deployment environment, smartphone versus Meta's GPU cluster, you know, very different. Secondly, consider the FM from perspective of your FMware as a black box, and you can optimize from there. So keep in mind that you have to maintain some kind of capability levels, But as long as you keep them there, you can do whatever else you want. If you want to use 20 small models and then run them as an ensemble and then majority pick the top output, if that's cheaper than running a whole bigger model and it still works, great, that's your solution. If you want to use 2 large models or 1 large model and that works but everything else doesn't, then what can you do? And last but not least, at least from my research and my attempts at this, I found that you really have to mix and match different methods to see what works best. Again, no one-size solution. You might pick something from one approach, something from another approach, combine them together, play around, test with the high parameters, and see if it works. So at the end of the day, this is, as some people used to say, machine learning is more of a science, more an art than a science. Similar thing, you have to, vibes-based development, unfortunately, but that's just the way it is. I think that's more or less it. Feel free to ask any questions here later, and thank you for listening.
Thank you, Kirill, for an amazing talk. Do we have any questions?
Yeah, very nice talk. So maybe a clarification question. Like we see there's something called mixture of expert model, right?
Yep.
And you're showing this router stuff. So is this router considered as a separate component outside of the mixture of expert, or these mixture experts just themselves internally also have a router? Yeah.
Right, yeah. So the difference is in this, when you're talking about a mixture of experts, these are typically a part of the single foundation model. So this is more in terms of in the actual architecture of the neural network. The routing that I'm talking about here, that's an external component. So there's 2 ways you can look about it. Some people have attempted to actually train these experts as part of the whole mixture of experts training, and these are individual separate models. The router component is when you can actually just pick and choose your individual LMs you want, and then try to find the most optimal one for you. So there's 2 separate things. Yeah, thank you. Anything else? Great, thank you.
Okay.